Hi, my name is Pacelli Bessa. Today I'm going to talk about stochastic HalfSpace theorems for minimal surfaces and H surface of 3. I'd like to think this is a joint work with Lucasio Jorge and Leandro Pessoa, my colleagues. And I'd like to thank Professor Hojo Lee for the organization of this festival and thank the audience too for the attention. Okay, I'm going to give you the motivation for my work. I'm going to present here. Eugenio Calabi in the 60 made two statements about minimal surface, hypersurface in Rn+1. First statement was, all complete minimal hypersurfaces in Rn+1 were extrinsically unbounded, not be inside a ball or something. And the second statement was, all complete minimal hypersurfaces, phi of m in m Rn+1, has extrinsically unbounded projection on any n-1 hyperplanes of Rn+1. In other words, if you project in some half space here, so it should be not in a ball. Calabi regarded later as an ambitious conjecture. He didn't have any idea if it were true or not true. But nevertheless, okay, in 1960, it gave us lots of motivation for research in minimal surfaces. And turns out that conjectures of Calabi were false. In 1980, Jorge and Xavier construct a family of complete minimal surfaces between two parallel planes. Lots of minimal surfaces inside the immersion of the disks. And years later, Nadirashvili, 1996, construct a complete, extrinsically bounded minimal surface in L3. This was a remarkable work. Nobody believed that Nadirashvili and anybody could just construct such thing. I mean, nobody believed that minimal surfaces were bounded at most, between two planes. Yeah, there was. Anyway, so once these questions were solved, I mean, Calabi conjecture was solved. The very first thing is, well, in 1980s, right, when they have this first family of bounded minimal surfaces, I mean, bounded in the sense that between two planes, the first question is, these surfaces has bounded curvature, or are these surfaces proper? So there's naturally, when you have this family of minimal surfaces between two parallel planes, you ask whether this has bounded curvature or if they are proper, meaning that pre-image of a compact set in R3 would be a proper in M. The first question was answered by Xavier in the following theorem. The convex hull of a non-planar complete minimal surface of R3 with bounded curvature is all of R3. Well, this was the convex hull theorem of Xavier, but in particular, you have that it could not be between two planes. I mean, because the convex hull of these two planes is the stuff inside the two parallel planes. So he answered the question whether you have when you have a minimal surface, a complete minimal surface in R3 with bounded curvature, it just have to be beyond any half space. So although we didn't have this name HalfSpace Theorems, but it was the first half space that we know of in the sense that cannot be inside a half space of R3, so defined by a plane. So cannot be a nice lab. Yeah, okay. So the second question was, I'm going to present here this definition, which is based on the work by Hoffman Mix, is the following. A class of minimal surface R3 has the half-space property if any surface in this class cannot lie in a half-space defined by a plane P unless it's parallel to a plane P. So you can rephrase the convex hull of Xavier's. The following says, or at least a corollary of Xavier's convex hull theorem is the class of complete minimal surfaces with bounded curvature of R3 has the half-space property. So this half-space theorem was only coined in 1990s with Hoffman Mix, beautiful result. I should remark that Rosenberg, Schultz, Spruck introduced a different notion of half-space property, but this is, I'm not mentioning now these things. Okay, So this is the idea with this notation. So if you have a class of surface, cannot be in a half space unless it's a parallel plane, you say that this class and this class has half space property. So the bounded minimal surface has the half space property. So Xavier's motivation was known to if the minimal surface in this lab has bounded curvature. Likewise, Hoffman-Mix wanted to show that the minimal surface in this lab were not proper. So they proved the following result. The class of complete properly immersed minimal surface of R3 has the half space property. So this language is very easy to state. So if you have a minimal surface, a properly immersed minimal surface in R3, it cannot be above a plane. It has to cross every plane you put it, it crosses the plane. So this is the half-space theorem, the famous very half-space theorem of Hoffman-Mix. Right? That opens many other questions. So around this time, in 1982, in fact, Mix, Simon, and Yao proved that the following result, given two disjoint, complete, properly immersed minimal surfaces, let's say M1 here and M12, then you have a minimal plane separating them. So once you have two properly minimal surfaces here, they have a minimal plane, unless one is a plane. Okay, so M1, M2, non-planar. So it must be there is a plane in between. So if you put together this Mix, Simon, and Yao's result, so you have a half space here, you have a plane here, you have a properly immersed here, then you have another two minimal surfaces, and then you have a plane. It could be not good. Let's say M1, M2, two properly immersed, and then you have a plane there. But you cannot be one M1 on a half space by this plane, so it should intersect. You cannot put two minimal surfaces. So Hoffman-Mix, in fact, proved more than what it was stated. They proved the strong half-space theorem that states that two complete properly immersed minimal surfaces intersect unless they are parallel planes. So this is the strong half-space theorem. So because once you have this Mix, Simon, and Yao's result, that you can put a plane between two properly immersed, and then you couple with this half space they proved before, then you cannot have two minimal surfaces properly immersed unless they are parallel planes, because otherwise you could put something there, it could not exist. So now, once you have the strong half-space theorem, so the first question is, and now, but you have Xavier's result. Xavier says that you cannot have a minimal surface with bounded curvature here inside in one half space. So this is the equivalent of Mix, Simon, Yao. So the only thing you have to prove is, in fact, you have to prove Mix, Simon, Yao's for bounded curvature in order to have a strong half space. So if you have two minimal surfaces with bounded curvature here, if you could put a plane inside, you can invoke Xavier's result, say that cannot be, so they must intersect. This was done in 2001 by Jorge and Oliveira and myself. Proved that the following: two complete minimal surfaces in R3 with bounded curvature intersect unless they are parallel planes. The work was just to separate them. So if you have two minimal surfaces with bounded curvature, we did not intersect, you can construct a plane inside between both. So you can ask Xavier's half space to say that cannot be. So this is the result in 2001. So this half space has been also okay. Also, I'm gonna mention that at the same time, Rosenberg proved in 2001, the same time, independently, of the same result. Say two minimal surfaces with bounded curvature intersect. But okay, but also ask the following question: once about, well, you have two properly immersed intersect, unless they are parallel plane. Two bounded curvatures minimal surface intersect. But what happens if you have a properly immersed and one of bounded curvature? We also were able to prove that they also, they could intersect. So they call the mixed half-space theorem. Now, stating a complete properly immersed minimal surface of R3 and a complete minimal surface of R3 with bounded curvature intersect unless they are parallel planes, right? Okay. Okay. Just to finish the remark here about this half-space theorems, let's say that there exist non-properly immersed minimal surfaces with bounded curvature of R3. In fact, there are many of them. Okay. Okay, right. Now I'm going to introduce the class of surface I'm going to work with, which is going to be the class of recurrent minimal surface. And then let's say just a few words about this Brownian motion stuff. This is very basic, and I won't get in any details of it. I'm going to just mention the least things that we needed for the proof and everything. Okay, I say a Riemannian manifold not necessarily complete, is recurrent if the standard Brownian motion, xt, visit any open set in arbitrarily large moments of time with probability 1. This is the picture here. So you start at x, the Brownian motion starts zigzag, zigzag, zigzag. Eventually, it reaches the open set U with chance 1. In fact, it keeps coming back every time the Brownian motion visit, get out, and so it visits infinitely many times with probability 1. So you have you find a sequence of TIs in the time going to infinity, so that xti belongs to you. Now, this is the definition. I mean, this is just a notion of what's a recurrent manifold, but you have lots of equivalents in geometric terms. The one I'm going to use is the following. Recurrent is equivalent to the following. So a recurrent manifold is equivalent to the Liouville property. Any bounded solution of any bounded subharmonic function is constant. That's what in a recurrent manifold. So when you have a recurrent manifold, you have any bounded solution, any bounded subharmonic function, it must be constant. That's the most treatable way to approach recurrent manifolds. Okay, let's say that the class of recurrent manifolds is quite large. For instance, all minimal immersions of C, all conformal minimal immersions of C in R3 are recurrent. Also, there is a paper by Ross Perez, Mix, says that complete properly embedded minimal surface of R3 with finite genus is also recurrent. And also surface with quadratic volume growth is also recurrent. So there is lots of minimal surface which are recurrent. But just for the record, Mark Voss and McGuinness Thomason proved that the Scherk first surface, which is one this infinite here, minus infinite there on the square, the black square of the chessboard, infinite chessboard is transient, which is not recurrent. So the Brownian motion doesn't go back many times. It comes sometime, but then goes away. So it doesn't visit every time, infinitely many times in the open set. Okay, and also we can find examples of non-proper recurrent manifolds with unbounded curvature. So the class of recurrent manifold is not inside of class of properly immersed or bounded curvature minimal surfaces. So the class we're gonna use here, gonna approach here, gonna study the class of recurrent minimal surface. It intersects. I mean, we have examples with bounded curvature. We have examples with properly immersed minimal surface. And also, we have examples which are not in this class. So we have, for instance, we can have a immersion of C in R3, minimum immersion of C, which is bounded curvature, unbounded curvature. It goes to minus infinity quadratically, and also has accumulation points in R3. In fact, four accumulation points only. It's a very pretty example. Okay, now our first result here I'm going to talk is the following mixed strong HalfSpace theorems between two classes: the class of minimal surface with bounded curvature and class of recurrent minimal surfaces. The statement is this: let M be a recurrent minimal surface and be a complete minimal surface with bounded curvature immersed in R3. So M has to be recurrent, not necessarily complete. And N has to be complete minimal surface with bounded curvature. Then they intersect unless they are parallel plane. Okay, let me say that there is a weaker notion than recurrence called stochastically complete. You can have other class of minimal surface, which is very large too, that includes all the recurrent manifold. They call it stochastically complete. Robert Neal, in a very beautiful paper, showed that if N has bounded curvature and N is stochastic complete, he showed that the distance between both are not zero. Okay, I'm going to have to assume that one of them is not flat, okay? But then the distance is zero. But he could not show that it intersect. And also, it cannot intersect in general because you have this construction by Atsuji, this Japanese mathematician. Atsuji showed that this construction of minimal surface in between two parallel planes by Jorge Xavier could be done where the surface is stochastic complete. So you have a stochastic complete manifold there between two planes and cannot cross the plane. Cannot cross the plane. But you can say that this is in the plane is recurrent. The plane is recurrent. The plane is stochastic complete. They cannot intersect the plane. So only the distance is zero. Okay. Now, I'm going to use for H surface the notion of stochastic complete. Now, I'm going to tell what is it, stochastic complete manifold. Okay, in general, a Riemannian manifold is stochastic complete if, for every x and every t positive, the integral of the heat kernel in the y variable is 1. So you can integrate on m the heat kernel pxyt on the variable y, and then you get 1, where this is the heat kernel. There is a stochastic interpretation for this number here, for this expression here, is the following. If you start with a Brownian motion at x in time 0, then the probability that to find the process xt in n at any time t is 1. If you integrate this instead of m, you integrate in u, in a subset, then this is the probability that the Brownian motion starts at 0 at x and to be found in u at time t, which the probability, the integral of pxyt at u. So, nevertheless, there are examples, many examples of stochastically incomplete manifolds, meaning if you integrate pxyt, it gets an integral less than 1. Examples of stochastic complete manifolds are in hyperbolic space, many-model space, bounded curvature, even surface with the quadratic decay of the intersectional curvature. And it means that the process goes to infinity in finite time. So the probability that the process disappears if it's stochastically incomplete is positive in finite time. This is the chance that the stochastic incomplete surface. The most beautiful example of stochastically incomplete are the bounded minimal surface by Nadir-Ashvili. Nadir-Ashvili, this bounded minimal surface, this counterexample Calabi conjecture, the integral of the heat kernel is less than 1. In fact, the average time that the particle goes to infinity, it disappears, is finite. It's bounded, uniformly bounded by one number that depends on the radius of the ball. It be there. Okay. Examples of stochastically complete surfaces: complete Riemannian manifold with quadratic decay, complete properly immersed submanifolds of Rn with bounded mean curvature. We can have also larger than this bounded curvature. It could be something bounded, not bounded, unbounded mean curvature, but with some control, goes to infinity. Complete bounded, cylindrically bounded minimal surface is incomplete. And also there is a Liouville property for characterization for stochastic completeness. It is equivalent to this following. For any positive lambda, any bounded solution to this equation, Laplace of u bigger or equal lambda u, is identically 0. This is also a very treatable way to approach stochastic complete in minimal surfaces. Okay, let me say something. Well, people start studying H surface, surface with constant mean curvature in R3. Well, and they have this kind of half-space theorem. It's not really half-space theorems, but it kind of, in some sense, they call this half-space theorems for H surface. So you have a properly embedded minimal H surface. So this surface divides the space in two pieces, one piece and the other piece, two connect components. And the mean curvature vector points to one region. And this region is called mean convex side of of N. N is the embedded, you have 2. The mean convex side is the side where the mean curvature vector points to. So what are the result in this half space for H surface? Okay, this is easy. You have a properly embedded H surface cannot lie in the mean convex side of another properly embedded H surface. Imagine H surface as a sphere of radius 1. So the mean curvature is 1. So we have here the H sphere. So you cannot put another sphere or another H or one surface there inside with the same in this mean convex side. It cannot fit. It has to be outside. Or inside, or it fits together both, or one crosses the other. Cannot be side on this because the H is the same. So basically, it open up. It cannot be. So if you have something inside, it has to be bigger. It has to be bigger. Okay. There is this result by Mix-Rosenberg say that an embedded complete H surface with bounded curvature is also proper. And we have this result here, which is it's a version of this other one here. This properly embedded H surface cannot be in the mean convex side of another H surface. So we're going to have the following. We're going to see when it's possible to be there, let's say. Okay, let's start with our N, which is a complete embedded H surface with bounded curvature. The same as here. Okay, N has bounded curvature. So you have immersed surface in the mean convex side of N. So N is bounded curvature, and here's the mean convex side. So you put a surface here. You put an immersed surface, not necessarily complete. Okay, if M is recurrent, cannot be, okay, so M cannot be in the mean convex side. M cannot be here once M is recurrent and the mean curvature, not the mean curvature, but the sup of the curvature of the absolute value is less than H, less or equal H. So if it's recurrent, it has to be less or equal, cannot be there. So it's forbidden, like the forbidden, or like this result is this previous result here. So here is this picture here. You cannot put a name here with this H surface with the same as N in this mean convex side. Okay. So our next result is the following. You have this embedded H surface here. Here's the mean convex side. And if you put something recurrent here, the mean curvature, the sup of the mean curvature has to be bigger than H, cannot be less than H. Okay, it has to be squeezed. And if it's stochastically complete, then the mean curvature the sup of the mean curvature has to be bigger or equal to H, cannot be lesser. Okay, then this is it's like an extension of not extension, it's just a version of the next or the former result for this this notion of stochastic complete and recurrent manifolds. Okay, let's give the proof of the proof is based on those two characterizations, right? For recurrent manifold, bounded subharmonic function is 0, and the other one is if you have a bounded solution of Laplacian of u plus lambda u bigger than a under u, then it's 0. Okay, let's say let's give you a sketch of proof of this result. Okay, what we're going to prove is M is recurrent. M is recurrent, is the blue one here, is recurrent. N is a complete mirror surface with bounded curvature, and then they intersect unless they are parallel flat surface. Okay, let's say they are parallel planes. I put flat surface because it could be a plane minus points, because the recurrent manifold doesn't need to be complete. But if you want to think it is complete, then you can think as of two minimal surface. Okay, let's prove it. To prove it, you assume on the contrary. Suppose they don't intersect. But, okay, suppose they don't intersect, then they are not parallel planes. Okay? If they are not parallel planes, one is not parallel plane. Then you can use Neal's result, say that the distance of them is 0. Because one of them is not a plane, but both are stochastic complete, right? Because they are bounded curvature is stochastic complete, recurrent is stochastic complete, and Okay. Then the distance is 0 in the sense that, okay, let's treat the first easy case that n is embedded. If n is embedded, then n is this black thing here, this picture here, which is black. Then since it's bounded curvature, you have in the embedded, you have a tubular neighborhood, epsilon tubular neighborhood for a small epsilon, depending on the curvature of n, so that this tube is embedded. Let's say that, and then I'm going to say that every here is a normal vector field. The mean curvature is K1 plus K2, and since H is minimal, K1 plus K2 is 0. Then in planar, so 1 is positive. Let's say K2 is positive. Since it's bounded, let's say C is the supremo of K2. Of course, since it's bounded curvature, K2 cannot be 2 plus infinity. The sum of K2 in K1 is 0, but it could be just very big, very big, very big. But since the product of them is bounded, it cannot be. So C is the supreme of K2 in N. Then I'm going to divide this tubular neighborhood in 2 pieces. One piece is U epsilon plus union, the boundary is N, and U epsilon minus. U epsilon plus is the one where N is pointing towards 2. Okay, this vector field n here. And I assume, without loss of generality, that m gets inside this tube. Since the distance is 0, so m is the blue thing, gets inside m. Okay, it could just get out, depends. I mean, but has to be close to and as much as we wanted, because the distance is 0. Okay, now I take the distance to n. This is a function t. T of y is this distance to the black surface here, this n here. Then I make this function f as log of 2 plus 2 epsilon plus epsilon c divided by 2 for ct y, and y is inside this u epsilon plus, which is going to be this reddish part here of the tube. Okay, then this is a function that is defined on this little tube, and if you go to epsilon, if t is epsilon, right? If t is epsilon over 2, then we're going to have log of 1, so this function is 0. And if t is bigger than epsilon over 2, since t is the distance to n, if I go a little bit out to epsilon, you get something negative. F is something change sign. So I restrict this function f to the blue immersion, which is this minimal surface here, m. So I call them U. It's just the composition with the immersion. So we're going to have the following situation. F is this function that's defined on the U plus epsilon. F is positive on this subtube, so epsilon over 4. And on epsilon 4, F is negative. And outside, F is F0 on the boundary of this U2, this tube, on the boundary of U epsilon 4. And outside is negative, just like this. Now, we just need to compute the Laplacian of U. So I'm going to here pick the picture. Since it's embedded, this is another picture. This is a zoom of this picture. So you have U epsilon here, the boundary of U epsilon. And my m is passing somewhere here. My m is get inside here. So I have a point here, phi of y, belongs to the surface. And I call z the foot. So it's the closest point in n of this point here in the ambient space, where in R3. And I just take K2 of z is the curvature of the principal curvature, the positive principal curvature of this point z in n, in C. So the Laplacian of this U in this point is bigger than 2c over 1 plus 2ct, which is distance between this and this, plus this expression here in k is nothing but the positive principal direction here, the eigenvalue of the principal curvature. If I take epsilon y inside the small, not u epsilon, but epsilon over 2, so where t is 1 over k, then Laplacian of u is bigger or equal to 0. So it's subharmonic in this little piece inside it. So for t y minus less than epsilon over 2, then Laplacian is subharmonic. But Now I have the following. I'm going to cut this function. So I have u, which is going to be 0 in epsilon over 4. Between 0 and epsilon over 4, u is positive. Then is negative. So I cut 0. So I have u plus as maximum of u and 0. And then I define this function u plus on the whole m. Well, the part fm that gets inside the tube is positive, but outside is negative. So I just stand as 0. I cut in 0. So we have here a bounded subharmonic function in the sense of distribution, but the Liouville property applies to this function. So u is constant. If u is constant, it means that t of y is constant, must be contained in a parallel surface of n. But if you have a minimal surface and you have a parallel surface and this is minimum, and it's because this is a plane to start with. N is a plane. Otherwise, this curvature here of this parallel surface would not be not 0. So M is parallel to a plane, and F is it, but M is not complete, necessarily complete. So I say that is this parallel, minimal surface parallel, but it's not complete. Maybe just a parallel surface, a flat surface to a positive distance. So that's the sketch of the proof in the case of the embedded situation. But the embedded situation gives you the idea how to prove it. We're going to take the distance to n, and then you compute a Laplacian of a function depending on the distance and show that it's subharmonic and bounded in the sense of distribution. Well, in the case of it's not embedded, you have intersections. You may have intersections, and also and maybe not proper. So instead of working of n, I'm going to take the closure of n. So it could be much larger. I mean, the closure of the accumulation points of n. So I'm going to take n bar as the closure. And I'm assuming that n is not all for R3. Otherwise, they will intersect, so nothing to prove. So if the closure of n is whole R3, since R3 has m inside, so it crosses, and then n cross n, and there's nothing to do. Now, let's assume, again, that the distance between m and n are 0, and they do not intersect. The idea is to construct a weak bounded solution, a subharmonic function in C2 W12 lock, and again, use the same function. Consider in U over to this function here, or t is the distance to the closure. U is the tubular neighborhood of not n, but the closure. And this function t is Lipschitz. That is not anymore smooth anywhere, because you have, so if you have like this, a situation is like this. If you have for every y in n, you have 2 feet. You can have more than 1 feet, more points. So the distance from y to n could be realized in many points. So it's not smooth, right? It's not smooth, but it is Lipschitz. It's continuous. It's Lipschitz. So I call this the feet. So all z in the closure of n, where the distance between y and z is this distance between y and n bar. Okay, we have many points. If you just take 2 planes like the second like this, and if you take a point here in the middle, you have here a circle of points. I mean, you have 2 points at least, 2 points at least. And if you have a cone, you have a circle of points distant, they're equidistant to this point y. Now, I'm going to just mention that everybody knows it, but I'm going to mention a function, a subharmonic function at a point, a function satisfies this equation in Barrier sense at a point. If there is for every delta, positive delta, you find a smooth function around Q, so that it coincides with age at Q and is less than age near Q, less or equal. And the Laplacian of this function, they call phi, delta Q, is bigger than minus delta at Q. So you have this family of functions where the Laplacian is smaller, almost non-negative, right? Almost non-negative. Is bigger than minus delta, and is below age. So you hear the graph of age, you have something touching behind it. Then we say that age is subharmonic in Barrier sense. Okay. So we need to show that this function that we just defined here before in the embedded case, this function u here, see this function u here is subharmonic in the Barrier sense. That the Liouville properties works for them too. So just to make notation easy, we identify y and phi of y. Then you have the situation. Let's say that n has a crossing like this. Right? So y in the corner here, I'm going to take the zoom. You're going to see that y has at least 2 points here as the phi. So here you have here in a little box. I say the box. This upper box here is a piece in u plus epsilon in this branch here. And this little box behind here is the c minus 2, c minus is the like the piece of u minus that I cut near y. So I fix z here. Instead, I just ignore the other foot. I take this foot here and I take an embedded neighborhood. Now I'm going to take not distance to n, but distance to vz. So in this neighborhood here, this function here has only one phi. So the distance is smooth. Okay, it is embedded. So the distance to this from z, I call this distance y to z here, is bigger than the distance to the closure, because closure could be closer, right? Bigger set. And that let's say tz is the distance between z to z, which is bigger to the distance to n. And I take a little ball around y, inside this little part which is positive. These two functions coincide in y, and then you can compute the function f, the same expression that you put t of z, and you have the same situation. So it's a setup for show that there is this function which has going to be Barrier sense. So this family of functions. So here's the situation here. I'm going to take the little ball here. The distance not to n, but to vz. So you can use the same expression t inside f, the same expression f. So you have this. Now you can make a little move here so we can avoid cut locus. So the distance to, in fact, to this. But in some sense, it's the same picture of the embedded case. It's more just detailed. And okay, resuming, just closing up, we have the function is smooth in a little ball near y. It's below f in u, and exactly equal to f at y. And then we need to show that Laplace of this smooth function is bigger than minus me, and me is very small. Then basically it's this. You have to only to show this. The calculation is the same, because then it's bounded harmonic function by Barrier sense, in viscous sense, and then you take the maximum, the same situation. So it finishes the proof. So it proves the theorem one. So it's a recurrent manifold in a bounded minimal surface. They intersect unless they are parallel planes. This is the theorem one. Now, let's go to the next theorem. So let's say n is an embedded H surface with bounded curvature. N is in R3. In particular, it's proper. Okay, embedded surface with bounded curvature is proper. H surface is proper. This is Rosenberg, mixed Rosenberg. An inverse surface cannot lie in the mean convex side, provided M is recurrent with sup of, this is L infinity, right? Not H, it's L infinity. It's the sup of the norm of mean curvature. And or is stochastic complete, and the sup is strictly class. Okay. N is properly embedded. We have the same function, f, the distance to the function to n. Then you can compute the Laplacian, and since it's not minimum anymore, appear this difference there. Then we can have lambda equal to the difference, and you see it's bigger or equal 0 if lambda is less than this. So you need subharmonicity. It's subharmonic if h minus sup is bigger or equal 0. And then if it's recurrent, then this has to be constant. U has to be constant. Or it has to be, and is bigger than something positive, which is going to be, again, h minus the sup, to use Liouville property. So basically, it fits up in the situation. It's very trivial. The computation, you get it's free. So, few words about these results. The defining characteristic of this class is stochastic nature. recurrence in stochastic completely. However, the method we use is very geometric, very deterministic. The difference between Liouville properties, bounded subharmonic function is constant, and bounded H subharmonic is zero, is highlighted in the intersection problems in these two classes. I mean, two categories, minimal surface and H surface. And this is all. Thank you so much for your attention. I hope everybody like it. I think Professor Hojo Lee, thank you, Kazanda. Bye-bye.